Okay, so we're going to this. So we know that what the sine theta. Sine theta is what? Measuring vertical distance from the horizontal diameter using the radius, right? Or as a fraction of the radius. Cosine is measuring horizontal distance using the radius, or it's a fraction of the radius, right? So we'll look at a different length here. So instead of the vertical distance up to this point right here, that's what we've been focusing on, right? We sweep the angle, that's our input, and we get a point, and we look at the vertical distance of that point. Instead, we're look at the vertical distance over there. So here, on the right edge of the circle, we're going to measure that distance up to the terminal side. So it's outside of the circle. And it's what? It's on the right side of the circle, tangent to the circle. So this right here, that distance right there, we're going to call tangent theta, because it's measuring along the tangent the vertical distance to the terminal side of the angle in radius length. So if we were to write out this definition, it would be tangent is the tangent function. Input is the same angle measure as before. Measure the angle swept counterclockwise from 3 o'clock position. Okay, the output is now going to be, it's also going to be a vertical distance above horizontal diameter in radius lengths, but now not up to the point on the circle, but along the vertical tangent on the right side of the circle. Vertical tangent. So we'll say the vertical line tangent to the circle at the 3 o'clock position. Let's do that again. So like in this example right here that I'm showing you, what's greater, sine theta or tangent theta? Tangent, see, it's a little bit greater. Do you see that? Because it's reaching up to, it's outside the circle, reaching up to the terminal side, whereas sine just reaches up to that point of intersection with the circle, right? Sine gives us a coordinate on the circle. You see? Sine gives us a coordinate on that y coordinate on the circle. Tangent is giving us this distance up to the terminal side along this 3 o'clock tangent. So as theta changes from 0 to pi over 2, what does tangent theta do? As theta changes from 0 to pi over 2, what does tangent theta do? What does it start at? 0? Does it increase or decrease? Okay, it increases. A lot or a little? A lot. How much does it increase? All the way. So here I am almost at pi over 2, and let's see if I can find where it intersects. It's intersecting at something like 28. So 28 radius lengths when it's almost pi over 2. And then if I got a little bit closer to pi over 2, what would happen? It would go even higher, right? So if we were to graph that, so we said tangent theta starts at 0, and then as you go from 0 to pi over 2, tangent goes from what to what? Starts at 0. Yeah, right. So as we get closer and closer to pi over 2, that thing is just gonna take further and further and further to get to intersect it, right? So let's take a look at that. So as theta goes from 0 to pi over 2, tangent starts at 0 and just gets very, very big, right? That's what I want right there. Okay, and then what happens then at pi over 2? How many radius lengths will it take along the 3 o'clock tangent to reach the terminal side if theta is at pi over 2? It's impossible, right? They're parallel lines. It'll never reach. Therefore, the tangent is undefined at pi over 2 because you can't reach that. You can't intersect it. But then what happens now as I go a little bit past pi over 2? Yeah, so the tangent's over here, so we have to extend the tangent down into the 4th quadrant and see where it intersects down in the 4th quadrant. So when I cross over pi over 2, then I got to take that line, I got to take it the other way, and down here I got to see where it intersects down here. So the tangent suddenly becomes very large negative. And as theta goes from pi over 2 to pi, what will tangent theta do? Go from what to what? So we'll start at a very large negative and go to 0. So increase up to 0. But at pi over 2, it's undefined, right? Because that 3 o'clock tangent will never intersect that terminal side at pi over 2. As soon as you move into the 2nd quadrant, we got to take that terminal side back into the 4th quadrant to get it to intersect the 3 o'clock tangent. So tangent becomes large negative. All right, what about in the 3rd quadrant? As theta goes from pi to 3 pi over 2, tangent theta will go from what to what? So here, watch it. Here we go. So as theta goes from pi to 3 pi over 2, tangent theta goes to from what to what? 0 to infinity again, right? It's just that we have to take the backside of the ray, right? The terminal ray is pointing to the 3rd quadrant. We take the backside of it to intersect that 3 o'clock tangent up in the 1st quadrant. And then when we get to 3 pi over 2, again, undefined. And then suddenly, when we get to the 4th quadrant, greater than 3 pi over 2, we get what? A really big large negative. And then as theta increases, we end up at 0 again. So this is this new function tangent theta. Okay, so does it matter how big the circle is? Why not? Why doesn't it matter how big the circle is? Because how are we measuring tangent theta? In radius lengths, okay? So it's the same thing as before. If you're measuring in radius lengths, then no matter how big or small your circle is, that number of radius lengths along the 3 o'clock tangent is going to be the same for any angle. Let's just see that in the 1st quadrant. Okay, so here's some angle. I can change the size of the circle. And that blue length will stay the same relative to the radius, right? So measuring it in terms of the radius will be the same. Just like sine and cosine, no matter what size circle you have, your vertical distance to the point on the circle, your horizontal distance to the point on the circle, remains that same fraction of the radius, no matter how big your circle is. Okay. So this is tangent theta. That's a quick overview. All right, let's then okay, so here I've got this So let's just look over here on the right side. So here I've swept this angle theta. And so let's make this circle bigger. Now let's do the car. We'll do the car. So there were some requests for the Lambo. Let's do the Lambo. Okay, so I've swept this angle theta. I'm not telling you what that angle theta is. The radius of our arc is 8.5 feet. And so after sweeping this angle measure theta, this puts the car some distance here to the right of the vertical diameter, which I'm going to say it's 3.5 feet. Okay, so now I want you to express. It's good review practice for the last couple weeks. See if you've learned anything. I want you to express the car's horizontal distance to the right of the vertical diameter as a fraction of the radius in two ways. So basically, we can express it one way, express it another way. So can you, in two ways, express how far that car is to the right of the vertical diameter as a fraction of the radius? Everyone should be able to do this. No calculator. You're writing out expressions, right? Expressions that two expressions that will give how far the car is to the right of the vertical diameter as a fraction of the radius. How many people think they have both? How many people think they have both? Oh, it's a sad day in pre-calculus. How many people think they have one way to do it? Oh, it's a super sad day. You can't express, given all the stuff I gave you, you can't express how far the car is to the right as a fraction of the radius? Okay, someone said 3.5 over 8.5. What do you think? So 3.5 over 8.5, the consensus is that's not right? I want to know how far the Lambo is to the right of the vertical diameter as a fraction of the radius. 3.5 over 5.5. No good? How many people think that's right? 3.5 over 8.5. How many people think that's wrong? How many people are here today? You should have raised your hand for that last one. How many people think that's right? 3.5 over 8.5 is expressing how far the car is to the right as a fraction of the radius. How many people think that's wrong? Okay, that's right. That's the fraction of the radius that it is over. It's 3.5 of 8.5. Get that? What is that? Find that in your calculator. What is that? 3.5 divided by 8.5. 0.4117. You see that's 0.4117, you said?
Yeah.
Okay, so it's like 41% of the way over. Or a fraction point, almost halfway over, 0.4117. Okay, how about another way to express how far the car is to the right of the vertical diameter as a fraction of the radius length? A different way to express that, same value. Please, somebody know this. Please. It doesn't sound familiar? The horizontal distance to the right of the vertical diameter as a fraction of the radius. It's no trick. I had you write that definition on 2 different quizzes. The horizontal distance to the right of the vertical diameter as a fraction of the radius is cosine of what? Cosine of theta. Cosine of theta. The horizontal distance to the right of the vertical diameter as a fraction of the radius. cosine with the input of the angle swept, counterclockwise from 3 o'clock. Okay, so I could take that 3.5 right there. Do you agree that I could take that and I could move it down onto the x-axis like that? Agree with that? Okay, and then I could, what would I be showing there? Vertical distance, okay? So I want you in 2 different ways. Well, no, I didn't give you that, so I didn't give you that. So we've got to figure out what that is. So I'm just going to call this, let's just call this x feet, okay? X feet and y feet. So it's something new now, something new. And then, do you see, so now we're making a triangle, and so what is this distance right here? What is that distance right there from there to there? 8.5. It's the radius, right? 8.5 feet. Okay, so now I want you to express the car's vertical distance above the horizontal diameter as a fraction of the radius in 2 different ways. And this will be easy. You all know how to do this now. So in 2 different ways, express the vertical distance above the horizontal diameter as a fraction of the radius. What's one way? Y over 8.5. The other way? Sine theta. Okay, so we're still focusing on the fact that all these things are measuring what? Horizontal distance and vertical distance as a fraction of the radius. We're just doing it different ways, as a ratio of the distance to the radius or using sine and cosine. So now I'm going to come in here and I'm going to say, looking at this right triangle, relative to this angle theta, this side right here is next to it. So we call it adjacent. And this leg over here is across from, in the triangle, across from theta. So we call it opposite. And in the triangle, that is called hypotenuse. So if 3.5 or x, so now we're going to talk something to x. If x feet over 8.5 feet gives us the fraction of the radius that we are to the right, or gives us cosine theta, what is that in terms of these sides of the triangle? It's going to be this length over this one will give us the fraction of the radius that we are to the right. So we're going to get adjacent over hypotenuse. And this one that gives us the fraction of the radius that we are up above the vertical diameter is that distance over the radius, opposite over hypotenuse. Okay, so this is where these triangle relationships come from. They come from our definitions of sine and cosine as vertical and horizontal distances as a fraction of the radius, right? That's what that's doing right there. Adjacent over hypotenuse is saying how far are you to the right as a fraction of the radius or the hypotenuse of the triangle, and how far up are you as a fraction of the radius or the hypotenuse of the triangle. Okay, so the meaning, so when we use now adjacent over hypotenuse, opposite over hypotenuse, all of our meanings that we developed are still preserved. In fact, that's where they come from. That's where these relationships come from. Okay, so let's go back and look at tangent. For tangent, so find this here. So for tangent, notice that, what is tangent? Tangent is, if I call this the length of this blue line, L, but like in feet or meters. Not measured in the radius, okay? What is tangent? Tangent is that length L measured in terms of the radius. So tangent theta is L over the radius length. Okay, it's measuring that distance and whatever the radius length is. Okay, so that would be L over R. That's what we talked about, right? So do you see that that is a similar triangle? That outer triangle is a similar triangle to our sine cosine triangle here? That tangent theta is also, what side is this? Opposite over adjacent by similar triangles, right? By similar triangles, that distance L in feet over the radius in feet is the same as whatever the length of the opposite is over the adjacent. Okay, so those are our so now we can use sine, cosine, and tangent then to work on triangles. Preserving the meanings. Opposite over hypotenuse. Opposite adjacent over hypotenuse. But it's not something different than before. Like I showed you, this is still measuring vertical height as a fraction of the radius. This is still measuring vertical height or horizontal distance as a fraction of the radius. It's just we're doing it with a triangle in the circle rather than just the coordinates and points. Okay, so flip open your book, your workbook. Module 8. Investigation 1. Okay, so what you're doing is you're given a right triangle. You're going to draw the circle. Okay? You're going to draw the circle. So let me just warn you here. This is what students have tried to do in the past. You get a triangle like this. They try to do this. It's like we're drawing the circle, and it's like, okay, here we go. Is that right? Okay, so just be warned. That's not right. So you have to get the configuration correct, okay? So, can make it better here. Your circle does not go through both of these points. So, make sure you draw the circle accurately relative to the triangle. And then answer the questions as laid out there. Answer those questions as laid out and take attendance. Work together.
You're doing this, but we're supposed to. Oh, wait, so that's still.
Okay, this is what you should have had for your circle. So how do we express? Actually, we're expressing what? BC in radius lengths or as a fraction of the radius. How would we express BC as a fraction of the radius? No, sorry, AC. How do we express AC as a fraction of the radius? 3 over 5, and that's the same as sine theta And 3 over 5 is the same as? What over what? Opposite over hypotenuse. Is that all they wanted to do for A? Is there any more to A? Is that so? We questions on that? So again, you're seeing it two ways. Yes, it's opposite over hypotenuse, but you're seeing that by doing 3/5, you're measuring AC using AB as its measuring stick, right? You're saying what fraction of the radius, what fraction of 5 is 3? What fraction of the radius 5 is 3? 3/5, 0.6 of the way, right? So sine equals 0.6, 0.6 of a radius length. Is B just the same? Is there any difference? Except different numbers? So what they want to do for cosine, then for cosine there's an added thing here. How are we gonna do it for cosine? Yeah, exactly. We're going to use the Pythagorean theorem to get that third side. Because if we're going to measure the horizontal distance, BC, in terms of the radius, we're going to need that in terms of whatever the axis units are, right? So what'd you get when you did that? 3.2? Somebody else get that? So you're going to get 3.2 using the Pythagorean theorem. And then if you want to express how far BC is as a fraction of the radius, it would be 3.2 over 4, which is our relationship, adjacent over hypotenuse, and it's the same as the value of cosine theta. Questions on that page? Okay, so that was all rigged because those were they were perfectly, first quadrant triangles. So this one isn't, right? So they're giving you this theta here. They want you to find cosine and sine. How can we do it? So this is like an angle, swept clockwise from 9 o'clock. So is everything different? What happens? How can we do this? So what if we looked at a symmetric triangle over here like this? What if we just flip that thing right over? Then would this also be theta? This would be 10.6. This would be 6. Is that 6.6? 6.6 and so by symmetry, these triangle relationships, they still work even if you're not looking at first quadrant angle swept counterclockwise from 3 o'clock. Because if we're going to do what? So how are we going to do cosine of theta? Cosine of theta is going to be? Right, so that's that horizontal distance over the radius. But if we look at our original triangle, it's still 8.3 is still which side? Adjacent side, right? Adjacent next to that. And 10.6 is still hypotenuse. So we can turn and flip and rotate these triangles so that it doesn't really match the angle that's swept. But these relationships, the adjacent and hypotenuse and opposite relationships, still hold for cosine, sine, and tangent. So what is sine theta for this one? Right, so opposite of the angle, cross over 10.6. Questions on that one? So let's look at So now, in this one over here on the, if you look to the right, so here's an angle beta, here's an angle alpha. So now, for this angle alpha, this is 6. Jump right off 6. So I want you to start by, for the angles beta and alpha, name the adjacent, the opposite, and the hypotenuse for each of those angles, because it's different. Adjacent is always the leg, the short, one of the short sides, that forms one side of the angle, one ray of the angle. It's next to it. The opposite is always the leg that's directly across from the angle. Hypotenuse is always the long side, opposite of the right angle. So first, identify what those lengths are, and then determine all these. With ratios, right? So use the ratios to write all these down. Okay, everyone's working on this? Whether you have a workbook or not, whether you're bored or not, everyone's working on it. I'll be right back. Okay, tell me what cosine of alpha is. You want 6 over square root of 40. Cosine of alpha.
Oh, cosine.
2? 2 over square root of 40, which is our hypotenuse. So now what happens is, we can use this relationship now to find the measure of the angle. If we have the cosine of alpha is 2 over square root of 40, we're asking what angle will give us that vertical distance to the right of the horizontal distance to the right of the vertical diameter. And what tool do we have that, given the horizontal distance, we want the angle? Inverse or cosine, right? Inverse cosine. And we got to be careful though, right? We've learned that this is tricky business with arc, cosine, and arc sine. But as long as we have angles between 0 and pi over 2 or 0 and 90, everything's safe, right? Because both of those ranges include 0 to pi over 2. So because we have angles smaller than 90 degrees, we don't have to really worry too much when we're solving these triangles, right triangles. What is the cosine inverse of 2 over radical 40? What's that? 1.25, and let's get it in degrees. So that's 1.25 radians. 71.5 degrees. So we can use the triangle relationships then to, if we have all the side lengths, we can use these ratios to solve for the angle in the triangle. the sum of angles in a triangle is 180. So this will be 18.5. So you could use arc sine or arc cosine to get the 18.5, or you could just do 180 minus the rest of the angles. Okay, questions on this problem?